In this video, we're going to look over a more complicated heat integration problem. Earlier, we looked at a scenario where we only had one hot stream and one cold stream. Now we have a more realistic scenario where we have two hot streams and two cold streams. So this is the setup. This is the problem that we have. We have our source temperatures and we have the desired target temperatures along with the heat capacity of each stream. In this video, the method that we're going to be using is called the composite curves. We're going to be drawing temperature enthalpy curves, and if you remember from the previous video, the slope of a temperature enthalpy curve is equal to 1 over mCp, which in our case for our first hot stream is just going to be 1. For our second hot stream it's going to be 2. 1 over 0.75, that's going to be 4 over 3, and 1 finally. So let's start off by representing H1 and H2 on a temperature enthalpy curve. Okay, so the first stream, our source temperature is 300 degrees Celsius and our target temperature is 150. Source temperature 300, target temperature 150. The slope is 1, therefore 6 down, 6 across. There we go. And that gives us our first curve, H1. And for our second stream, it goes, our source temperature is 200 and our target temperature is 50. So 200 and 50. All right, and the slope of the line is 2. We have 6 down, 3 across. Okay, let's see. All right, there we go. So right now we have both of the individual hot streams. What we want to do is we want to look for intervals where these streams cross temperatures. If you look at the interval 200 and 150, in this interval you encounter both of the streams. So what we want to do is we want to combine the streams that occur in the same temperature interval and make one single composite curve instead of two individual temperature enthalpy curves. So in order to do that, go back. All right, I'm just going to keep this one. And for this segment, now your new slope is going to be 1 over mCp of the first stream plus 1 over mCp of the second stream. So as many streams as you find in those interval, you want to add them. You want to add their heat capacities, and the inverse is going to be the slope. So in our case, that's going to be 1 over 1 plus 0.5, which gives us 1 over 3 over 2, 2 by third. Therefore 2 down, 3 across. And finally we have 150 here. So this region is where you have both of the streams in this temperature interval, both of the streams occur. Finally, we want to go from, okay, so 5, hold on a second, 2 down. Let me just fix that real quick. So this is a real test of your graphing skills, and like in order to get an accurate answer using composite curves, your graphing technique needs to be as precise as possible. The method of composite curves works better if you have like a graphing software or a computer program, but it's still valid. Like if you can do it on a relatively like what I'm doing, like I'm finding the slopes and I'm being like very accurate with my drawings, and like make sure you just like keep refining them. So the two things that the composite curves are going to tell you, actually the three things that the composite curve is going to tell you, is the location of delta T min, the minimum utility requirements, and the minimum heat exchanger area. So those are the three things that you can find from the composite curves. Okay, now we have the composite curve for our hot streams, and below here I've done the same for the cold streams. I found the intervals over which both streams occur, and I've like combined them into a single curve by adding their heat capacities. Okay, now once you have both of your composite curves, your hot curve and your cold curve, the next step is to find the location of the pinch point or the delta T minimum. So what you want to do is, and you want to start off by assuming a minimum approach temperature, a pinch of 0. Now depending on your minimum approach temperature, you can move this either left or right, not up or down, okay, just left or right. So if I keep moving this towards the left, I want to keep moving this until both curves touch. Okay, so at this location you can see here, whoops, at this point at temperature of 100 degrees Celsius, we see that both curves touch. Now, all right, next step, we know where both of these curves intersect each other. Next step is gonna be, whoops, let me try to get hold of this. All right, okay, okay, we're just having a little bit of difficulty here, sorry about that. Okay, now let's suppose we have a now the minimum approach temperature is always going to occur above the cold stream temperature of 100 degrees Celsius. So if I want to assume a minimum approach temperature of 25 degrees Celsius, let's say, each of these increments represent an interval of 25 degrees Celsius. So I'm just going to take my cold composite curve and move it towards the left hand side until it's directly 1 unit below the hot stream. So in this case, let's see, right here, the minimum, the delta T between both streams is 25 degrees Celsius, and that's the location of our pinch point. Now finding the location of the pinch point is important because like it's gonna help you determine how you're gonna be matching streams for different heat exchangers. There are different rules for matches above the pinch point and different rules for matches below the pinch point. So let me highlight the area for our heat exchange. So the area in yellow is gonna be the temperature range and the enthalpy range over which you can exchange energy between both of these, between both the hot streams and the cold streams. And on the hot side right here, we have the heating requirement. That's gonna be your minimum heating requirement right here. And on the cold side at the bottom, you're gonna have your minimum cooling requirement right here. This is the minimum heating requirement and the minimum cooling requirement for a minimum approach temperature of 25 degrees Celsius. And obviously, like, once you know these temperature intervals you have this continuous segment, you have another continuous segment over here, and another one over here. This is going to help you determine the minimum area required for the heat exchangers. All right, so let me just quickly find what our heating and cooling requirements were for this case. Our Q heat was equal to our temperature difference is it's going from roughly 265 to 300. Minus 265, and the heat capacity was 1. So that's your heating requirement for this, the minimum heating requirement for this heat exchange network. And the cooling requirement is, this needs to go from 75 degrees Celsius to 50 degrees Celsius. That gives us our cooling requirement. And once you know the locations of these intermediate temperatures between the continuous segments, you'll be able to find the minimum area of the heat exchanger that goes with this network. Now, the accuracy of the composite curves, like I said, is heavily dependent on how precise you can make your graphs, and it can be, as you saw, it can be quite tedious at times. In the next video, I'm going to show you a method that is more algorithm based and does not rely on graphing techniques. Right, so stay tuned.